So let's do another example. In this case, I have 3,000 cubic meters per day of a gas mixture containing methane and N-butane at 21 degrees C, and these are entering an absorber tower. The partial pressures at these conditions are 103 kilopascals for methane and 586 kilopascals for N-butane. In the absorber, 80% of the N-butane will be removed, and the remaining gas leaves the tower at 38 degrees C and a total pressure of 550 kilopascals. What is the volumetric flow rate of gas at the exit, and how many moles per day of N-butane are removed from the gas in this process? We're going to assume that it's an ideal gas, but we're going to verify our assumption. So in this case, we are working a material balance problem. Basically, I have the gas mixture that comes in at 21 degrees C under the conditions stated there, and it's going into an absorber tower. It's going to leave, there's going to be one stream that's going to be just N-butane, okay, and there's going to be another stream that's going to be the remaining gas. And that is going to be exiting at 38 degrees C. We want to know what's the volumetric flow rate of the gas and the remaining gas at the exit, and how much N-butane is removed here. Now, I have numbered these streams for the sake of calculations. I did 1, 2, 3 as my stream numbers. We're going to assume an ideal gas, but verify the assumption. So we'll come back and do that kind of at the end. But this is a basic material balance problem that we're going to attempt to solve. So let's start looking at our procedure. So I have mole fractions of each substance given. I'm going to have CH4 and NC4H10 are my two substances. They are in streams 1, 2, and 3. Okay. I have the amount of each substance. I called them M and B for methane and butane. And my stream 3 is pure butane. I have a total flow rate of each of these in moles. And in volume. And I have the temperatures and pressures given. Now, they did not specifically tell me the pressure of stream 1, but they told me the partial pressures of the two components, and I can add them up to get the total pressure. I also know that the material leaves at the same pressure. Both streams will be at the same pressure for the process. And then I have some process specs that are given in the problem statement. I know that XM1 is going to be based on the fact that, well, okay, PA is YA times total pressure. So XM1 is going to be 103 out of 689, and XB1 is going to be 586 out of 689, right? I also know that PM plus PB equals the total pressure for any particular stream. I also have the fact that I know that 80% of the butane will be removed. So F3 is going to be 80% of the amount that came in, XB1 times F1. And since I'm assuming an ideal gas, then I also know that PV is equal to the flow rate for any stream times RT. So this is my basic information that I have here. Now the material balances for CH4, there's no reaction, so XM1F1 equals XM2F2. All of the methane goes out in stream 2. And for the butane, I know that the amount that comes in leaves as either a component in stream 2 or in stream 3. And I also have the total that F1 equals F2 plus F3. And I've got my sum of X equations. So XM1 plus XB1 equals 1. XM2 plus XB2 equals 1. So I now have all my equations. I have quite a few unknowns, but this isn't really too hard to solve. So I can solve for XM1 and XB1. Oh, let me change color there. I can use those two to find my equations. And this is 0.1495. So 0.15 roughly, and the other one is 0.85. Okay, so I have that. Okay, I have XB1. If I have XB1, I know this. I know XM1. I know the total volume there, so I can use the ideal gas law on stream 1 to find out that F1 is 689 kilopascals times 3,000 meters cubed over 8.314 times 10 to the minus 3 meters cubed kilopascals per mole Kelvin. And the temperature, oh, I didn't correct those yet. So 273 plus 21 is 294 Kelvin. And so F1 is equal to 84,635 moles. So 846,000 moles or 846 kilomoles. Next, after this, I can use that. I now know F1, and so I can calculate F3. XB1 is 0.85 times F1. And so F3 is equal to 575,376 moles. Okay. So once I have F1 and F3, I can find XM3. Oh wait, XM3. I knew that. That was that's XM2. So I have that. I can find F2. Okay, and once I have that, then I can find XM2 equals XM1 F1 over F2, and XB2 equals 1 minus XM2. So I've got all of my answers. I can find V2 using the ideal gas law. I'm not going to write all of these details down because they're starting to get a little boring. Okay, V2 is going to be 1270 meters cubed. V3 is going to be 2705 meters cubed. Okay. One thing that's really important to note is that V1 is not the same as V2 plus V3 because the temperatures and pressures are different. Okay, so what were the questions that they asked? They asked how many kilomoles per day of C4H10 are removed. And that's this answer right here. So 575 kilomoles per day removed. And what's the volume of gas that leaves per day? That's V2. That's the other question that they asked. Now they did ask us to verify whether or not this is an ideal gas. So to do that, and I failed to, I'm sorry, in my write-up I did not do this one. You're going to have to do the same thing where we're going to take our mole fraction, so 0.15 times Tc of methane plus 0.85 times Tc of butane. Okay, this will get me the Tc pseudocritical. Take that and divide it into 294 Kelvin. And you're going to find your curve here. Now that's not the correct value. You're going to find your pressure, and what you're going to find is indeed this is going to be an ideal gas. Now, one thing about when you check for a Z, frequently when you work problems, you're not able to determine Z up front. And so if we found that this were not an ideal gas, if we found that Z was like 0.9, then I would need to go through and redo everywhere I had a calculation that involved the ideal gas law. So this step here, this step here, this step here. And I'd have to incorporate that value of Z. Unfortunately, if I did that and then checked again for what the value for Z is, probably it wouldn't come out to be 0.9 this time, because I'm having to do this in sort of an iterative approach. Now we're going to hold this for future courses, but just be aware that a lot of times we have to make an assumption and then check at the end whether or not it is true. If it is not true, we then would go through and correct our calculations. So problems can start becoming very long. Now this concludes Chapter 5. In the next set of lessons, we'll be looking at what to do when we have mixtures.